Hi guys, welcome back to Data Every Day. Today we are looking at a dataset of blood cell images. So we have, there's two datasets here. We're going to be using dataset 2, which has the images more nicely labeled. In here we have 4 different classes, which are different types of blood cell. And each one contains images, 320 by 240 I believe, images of blood cells. And we are trying to predict which class of blood cell a given image belongs to. So let's hop into the notebook. I'm going to be using NumPy just for messing around. If we ever want to do computation, it's very nice to have. Then for visualization, I'm going to be using Plotly Express, PyPlot, and Seaborn. And then we'll do the training with TensorFlow, and I'm just importing accuracy score and classification report from sklearn.metrics to analyze the model's performance. So let's go ahead and import all of that, and we're going to get the train directory and test directory for our data. So in here, we have train and test. We can grab the file path. I think I actually should get an image, and then call that traindir, and delete down to train. And tester is going to be the same thing except test. Whoops. Alright, so there are our directories, and now we'll go ahead and load in the image data. For this we're going to be using generators, and generators are nice because it prevents you from having to load up all the images onto the disk, from the disk, which can really it can clog up your memory. It can actually crash the notebook if we run out of memory. So a generator will load them in a few at a time, train on them, and then recycle the memory so that we don't run out. So let's create the generators. And we'll create one for training called traingen, and one for test data called testgen. Both of these are going to come from Keras, tf.keras.preprocessing.image data generator. And we're going to be using a transfer learning CNN today, so we're going to be using a pre-trained model, actually the MobileNetV2 model. So let's check this out on Keras. I'm going to pull up the Keras documentation right here. And MobileNetV2 is what we're going to be using. It's basically a convolutional neural network that was trained on the ImageNet dataset. And so it's very good at extracting features. We're going to do include top equals false, which means take off the classification part of the model. So we're just going to use it as a feature extractor. And then once we've extracted the features, we'll include our own classification classifier on the end of the model. Now I would like to point out that each Keras application expects a different kind of input preprocessing. For MobileNetV2, call this function on your inputs before passing them into the model. So if we look at this, this function is going to be used to preprocess the data, and it accepts a NumPy array or TF tensor with 3D or 4D with 3 color channels and values between 0 and 255. So that's the format of our images. So we don't want to apply any rescaling or anything like setting the values between 0 and 1, because this function will take care of everything. We just have to pass it in as it is. And you can see you can actually include this in the model flow, in the model construction. But another way to do this is to do it right in the generator. In here, we can specify a pre-processing function, and we can pass in, I want to get this guy, pass in that. So we're going to actually apply the pre-processing right as the images are taken from the directories. Now, only thing else I want to do is for the train generator, I want to give it a validation split. I want to get our validation data from the train directory. So I'm going to send 20% of it to the validation set, and the other 80% will be used for training. Then we'll flow the image data. So by flow, I just mean we're going to specify how we want to pull the images from the folders into our environment. So for this we'll use flow from directory, which is a convenient method from Keras. It's actually tf.keras. It comes from traingen. So TrainGen has a method called flow from directory, and we'll store the result in train images. Now we specify the directory we want to flow from, and that's going to be our train dir. We'll specify the target size. This allows us to resize the images. MobileNet originally took 224 by 224 images. Now I believe we can resize them as long as they have 3 color channels. But I'm going to keep it. I'm going to resize them to be the original shape that MobileNet was trained on. So 224 by 224. So I'll pass that in here. Then we'll specify a color mode, which is RGB. That means it has 3 color channels. And then a class mode. So our classes are categorical. We have 4 classes. It's a multi-class classification. So I'll type categorical in here. We'll specify a batch size, where what size batch do we want to flow the images in. Then make that 32, and I'll keep shuffle equals true on. This is important when you're doing training, that you shuffle the image order. The seed will ensure that the shuffle is always done in the same way. So seed equals 42, and then the subset will be training. So the subset comes from the validation split. Now if we just copy this over, and we change this to validation image, val images, we're still flowing from the same train generator, the same directory, but the subset becomes validation. And so now 80% of the directory will go into here, and the other 20% will go into here. The last thing to do is the test images. So this is test images. This one we're actually going to flow through TestGen. So this one doesn't have a validation split. TestGen. The directory is going to be testdir. That's our test directory, right? Then everything else is the same, except shuffle must be on false, because we don't want to shuffle the order of our test set. First of all, it doesn't matter if we do, and it can we can mess up the labeling of the images if we shuffle it. So we'll leave it with shuffle equals false, and I'm going to remove the subset aspect. Alright, so we're flowing in the data. It's counting up all the images and seeing where they belong. And you can see the train set has this many images, and they all belong to 4 classes. Validation has the fewest, and test has 2,400 images. Alright, so let's build a pre-trained model. So I'm going to call this pre-trained model, and this is going to be our MobileNetV2. So we actually just grabbed this. You can see what it takes. I'll also grab that. And we don't need to specify the input shape. I guess I will anyway. 224 by 224 by 3. Alpha we'll leave out. Include top, we're making sure this is on false so that we remove the classification aspect of the model. We're going to keep the weights as ImageNet. We're going to remove input tensor. Pooling, this allows us to add a pooling layer to the end of the model without having to do it manually. So we can type average for global average pooling. And that will, we could always put that on ourselves if we wanted, but this is sort of, it has the effect of reducing the output from 2 dimensions into 1 dimension. So we have a final vector of features that we can use for classification. Now classes is only used if you have include top equals false, equals true, so I'll remove that. And this as well, classifier activation, not being used. So here we go. Run that. Now there's one more thing we have to make sure, is that we set pre-trained model dot trainable to false. And this is because we don't want to train the weights associated with this part of the model. They've already been optimized to extract features from images. ImageNet is a huge data set of 1,000 different classes of images, and these models have been trained to be able to extract features from almost any image you give it. So we want to make sure that those weights stay intact, so we're setting trainable to false. Alright, and then we'll build the classification model. So the inputs to our classification model are going to be the inputs to our pre-trained model, because we're going to send the image into the pre-trained model first, and first it will have this pre-processed input, preprocess input function applied to it. Then it will be sent right into our pre-trained model. So we're going to set the inputs equal to pretrained model.input. Then we'll have a dense layer, a hidden layer, just to increase maybe the classification accuracy. So this will be a dense layer. We'll give it 128 neurons and a ReLU activation. And then we'll pass in not inputs, because that's actually the input to the model, but pre-trained model dot output. So the inputs will come through the pre-trained model, then it will run through the whole pre-trained model, and then you get the output here and pass that into X. Then our outputs to the whole model are going to be another dense layer with our classes. So we have 4 classes, and we give it a softmax activation to produce probabilities that sum to 1 spread across the classes. So the class with the highest probability will be the classification. Then this takes in input from X. Alright, and then we'll create our model with tf.keras.model. The inputs will be inputs, and the outputs will be outputs. We'll then compile the model. We're going to use an atom optimizer. And for loss, now we have to be careful here. We could do sparse categorical cross entropy, which is the typical loss function to use when dealing with multi-class classification problems. But if we look at the image data, let's say we look at trained images, and we take one batch. We can do that with next. We grab the next batch, and then we look at the labels only with sub 1. So if we do sub 0, we'll get the image data. If we do sub 1, we'll get the label data. You can see that the labels are in one hot vector form. And because they're in this form, because the label is not specified as an integer, but specified as a whole vector, we have to make sure that we go down here and remove the sparse. So we're only doing categorical cross entropy. Otherwise, we'll throw an error. The reason it's called sparse in the case of integer labels is because when it's converted into one of these one-hots, an integer label will always be a one-hot vector. For this case, we could actually have a 1 here and a 1 here, so it wouldn't necessarily be sparse. You could have multiple ones within a single vector. But when doing integer labels, it's guaranteed that you'll have a sparse encoding. Okay, so last thing is metrics. I'm going to include just accuracy since it's multi-class, and then we will print out a summary of the model with model.summary. Alright, and here you can see, so we have quite a big model, and none of it we created. This is the only part of it that we actually added to the model. Everything above it is built from the pre-trained model. You can see it comes in as the image size. All sorts of transformations are applied with convolutional layers and others. And then finally at the end it comes down into a single vector of 1280, and then that gets reduced to 128, and that gets reduced to our final 4 class probabilities. Now we'll do the training. And for this we're going to store the results of our training in history and called model.fit. And we're training on the train images. So I'll pass in train images. We'll give it some validation data, and that's coming from val images. Then the epochs. What we'll do is train for a bunch of epochs, 100 epochs, and specify a callback function, which is early stopping, which comes from Keras. And this callback function just allows us to not have to worry about when the model starts overfitting. This will automatically stop the model from training when it starts overfitting and restore the best weights, the weights from the best epoch. So we specify a value to monitor, which will be validation loss. And when it notices the validation loss stops improving, when it starts rising again, it will stop the model from training, but only after a certain patience value number of epochs that we specify. So how about we do 3? When it sees the model stops improving for 3 epochs consecutively, it will stop the training and it will restore the weights from the best epoch with restore best weights equals true. Alright, we'll run this. And then after that, I'd like to create a plotly figure. Oh, you know what I should do actually? I have to train with GPU acceleration. I mean, I don't have to, but it really speeds up the training of image classification. So accelerator, GPU, I'll turn it on, and I will restart the notebook as soon as this finishes. In the meantime, I'm going to create a plotly figure with px.line, so that's plotly express dot line. And we're going to grab the history of the model. Let me just run all this. So history is where we stored the model. And history, this history object, has a dictionary called history associated with it. So history.history gets a dictionary of all the losses and metrics of the model over the course of its training. So the keys in the dictionary are the metrics. You will have loss, accuracy, validation loss, and validation accuracy. And so the values associated with each of those keys are actually lists of the metric values over time for each epoch. So Y here is going to be drawing keys from the dictionary we specified, and it will plot their values. So the keys we want are the loss, which is the training loss, and the val loss, which is the validation loss. Then we'll give it some labels. On the x-axis, which is index, we'll map that to epoch. And on the y-axis, which is value, we'll map to loss. And we'll give it a title as well. This will just be training and validation loss over time. And we'll show the plot. So this is still going. I will run this afterwards. In the meantime, we can start writing the code for the results. So before we run, we write the results code to check out how the model is doing. I'm going to get the class names, store that in a final variable like this, which will just come from if we take the image data it was trained on, train images, and take the class indices attribute. This will return a dictionary mapping each integer to its class name. Each class name to its integer. So we can get the actual class names in the order that we want them with .keys to get the keys of the dictionary, and then turn that whole thing into a list. We'll print that out when it finishes. In the meantime, we will start creating the confusion matrix to see how the model's doing. So first we'll generate a set of predictions, and that will come from model.predict. We're going to predict on the test images. So we make our predictions on the test images, and this function will return a two-dimensional array of probability values, where each row represents a different test example, and each column represents a different class. So we'll have a what was the number of test examples? 2,487. So we'll have a 2,487 by 4 array, where each value in a single row, each of the 4 values, is a probability estimate for each class. And so for a given row, the class with the highest probability is going to be our classification. And we can use numpy.argmax along axis 1, which is the column axis, to, for each row, go along the column axis, find the highest probability, and return the index of that probability. So return the spacing, like which space it's in. And that will be that's a convenient way to get the probability values as actual classifications, as integer classifications. Then once we have that set, this is just a list or a NumPy array of integer classification values. Then we'll get the accuracy using accuracy score from sklearn, which I imported earlier. This is going to take in the true values, which comes from test images.labels, and the predicted values, which comes from predictions. Then we'll compute a confusion matrix using confusion matrix. No, actually, we're going to use a TensorFlow confusion matrix function, tf.math dot confusion matrix. And this is also going to take in test images dot labels and predictions. Lastly, we'll have a classification report, which will just give us like precision and recall metrics for each class. And so for this, we're going to use classification report from sklearn. This also takes in test images dot labels and predictions. We also specify a target names here, which is we want to just show the names of the classes, and that's going to come from class names. Okay, and then we'll print out the test accuracy, and this is we'll display it to 3 decimal places as a percentage, and format that with ACK times 100 since we want to see it as a percentage form. Then we'll plot out the confusion matrix with Seaborn. So we'll create a pie-plot figure with a figure size of 8 by 8, and then call Seaborn's heat map function, and get a heat map for CM, which is our confusion matrix, and turn on annotations so we can see the actual counts for each classification, for each box in the heat map. Then we'll specify format equals G just to ensure that the counts are coming up as integers and not in scientific notation. We'll set the minimum color value, which will be 0, which is the minimum value that one of the annotations can have. Then we'll give it a color map, which is blues, and we'll turn off the color bar with cbar equals false. Alright, and then we're going to plot, we're going to set the tick marks on the heat map. So with plot.xticks for the x-axis tick marks, the ticks, which is the spacing of the tick marks, we're going to get that with a numpy a range. And we want 4 a range values that will give us 0, 1, 2, and 3. And we want to shift those over by 0.5 so that the ticks lie in the middle of each box. Then the labels will also be class names. So we want to display class names on each axis. We're going to do exactly the same thing for the y ticks. Alright, then we'll give it some axis labels. The x label will be the predicted values, and the y label will be the actual values. Then we'll give it a title. This will be confusion matrix, and we'll show the result. So this might finish soon. The last thing I want to do is print out the classification report. So I'll new line that with a bunch of hyphens. We see something. Oh, it finished. Okay. All right. All right. Let me just print this in. And I'm going to include CLR here, which is our classification report. And this should do it. So what I'll do, now that it's finished training, we're going to look at the history. You can see that the training loss keeps going down. The validation loss also is going down, but at some point it starts overfitting and increasing. And the early stopping callback kicks in, notices it's going back up, and immediately goes back and restores the weights from the best epoch, which had the lowest loss. Then we'll get our class names. Here are our class names in the order we need. And then we'll make predictions. And we'll see how we're doing. So just taking a moment to make the predictions, and then it should display everything properly. Alright, here it is. So this is a bit alarming to me. We're not doing so well, especially within the neutrophil column. The other columns are looking okay. These classes are looking decent. You can see within a class, our predictions are more or less in line with the true values within all these first 3 classes. But the neutrophil column, we have a lot of misclassifications. It is finding most of them correct, but it's predicting a lot of the other ones as neutrophil when it shouldn't. And I say shouldn't here because we look up here and our validation accuracy is in the 80s and 90s. And if we go up here, just to verify this, if we take our validation images and I turn shuffle equals false, and I just reload these validation images with no shuffle so that they're in the right order, and then I come back down here and I do the same thing but on the validation images. So I specify val images instead of test images, and we run this. We should see something more in line with this kind of result. And sure enough, we get a 92% accuracy, and it's almost perfect. So the reason I think this is alarming is because the test set is supposed to mimic the training set, or maybe the other way around. They're supposed to be drawn from the same distribution, from the same data generating process. And when you see the model doing substantially better on the validation set than it is on the test set, it's possible that the test set has been mislabeled, or the test set is drawn from some other data generating process than the original train set was. And so sometimes when you get a pre-split data set like this, where it's split for you, you can't guarantee that the images in the train set are the same as the images in the test set. What I mean is the same quality, the same type. So maybe, especially because this neutrophil column has some problems with it, maybe, I mean I can't tell with my eyes, but these might be mislabeled, or there might be other classes mixed in with this that's confusing the model, but just on the test set. So I can't be certain, but it is alarming to see that we're doing so well on the validation split, but then when we evaluate it on the test images, we are doing much worse with a 50% accuracy. Alright, but that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.